Hey again. So I'm back with a quick summary of this week's Edgenuity lessons. So this week in Edgenuity, you needed to go over mirrors, lenses, and diffraction for light. So I'm making a quick video summary of that stuff. Everything in this video is the stuff that I will potentially quiz you over. If there's anything that I'm not covering here, then it's not going to be on your quiz. This is not intended to completely replace any practice or examples you may get in Edgenuity. You may find this to be a little too quick, but I am going to go over all the most important concepts. So I'll start with mirrors, just like Edgenuity lesson does. So a mirror, you guys are all familiar with a mirror. You see one I bet every single day. A mirror reflects light. So a mirror causes you to see a reflection, and it reflects light in such a way that an image can be seen. There are ways to reflect light that will not generate an image. And there are, of course, different shapes of mirrors. The shape that you are most familiar with is a plane mirror. Those are flat mirrors, so like in your bathroom. A plane mirror will always produce a virtual image, an upright image, and an image that is the same size as the object. So have you ever noticed that when you go in your bathroom and look at the mirror, you never see yourself standing upside down? It doesn't look as though you're hanging from the ceiling when you look at your mirror. So it's an upright image. You appear to be inside of the mirror as well. So when you go in the bathroom and you look in the mirror, you're seeing your reflection and it looks like you're inside the mirror. That tells you it's a virtual image. You never see your reflection projected onto the wall next to you. That would not be a virtual image, and that would not be a plane mirror. And you notice that when you're standing in front of the mirror, you look the right size. If you're really close to the mirror, you appear to be right there, really close to the mirror. If you're far away, your reflection is really far away inside the mirror. You never look gigantic in the mirror, and you don't look tiny in the mirror. You look the right size. So a plane mirror will always produce that kind of image. So maybe it's important to know what you're going to see in a plane mirror. Also, a plane mirror will always show you left-right reversal. You've probably noticed at this point in your life that when you look in the mirror, if there's something, let's say, written on your shirt, it's going to look reversed in the mirror. That's why we call it mirrored when things are like that. So a plane mirror will always flip something left-right. Now, there is, of course, other shapes of mirrors. We have concave mirrors. These are mirrors that are curved inwards, like this picture shows you here. So the inside of the mirror is, the inside of this shape is the mirror. So the inward curved part is where the mirror actually is. And this curvature causes all the light that hits the mirror to get focused into one single spot. So each of these lines represents a light ray. They all hit the mirror and they're all bent and sent right into this one spot right there. That spot where all the light is focused is called the focal point. So it's labeled F. So the focal point is where the mirror is going to make all the light go through. And since it's making all the light come together at a single point, we call that converging. So converging means they all come together. These mirrors can make images that are larger or smaller than the way the object normally looks. They can make images that are real or virtual, meaning images that could appear to be inside the mirror, like you're used to, or images that can be projected onto something. And they can make images that are upright or inverted. I had an example of one of these mirrors. It's a fairly large mirror that I would have brought around the class and shown to you. As I get closer to you, you would look normal, you'd get bigger, like you were magnifying, and then suddenly you would flip and you would see yourself upside down. So these mirrors can change what you are seeing because they're curved. And of course, we have the opposite. So what if the mirror was bent outwards instead of inwards? This is called a convex mirror. These mirrors are bent outwards, and these do the opposite. Mirrors that are curved inwards cause all the light to come together. So they're converging mirrors. These do the opposite. These will cause the light rays to all go apart. They cause them to diverge. So Converging means come together. Diverging means go apart. And since these light rays never actually come together at any point, these mirrors will always create virtual images. So that means you will always see an image that appears to be inside these mirrors. So let's talk a little bit more about these images that I keep talking about. I mentioned before that an image can appear to be upright or inverted. When you look in a plane mirror, you're standing upright. It's normal. But there are mirrors, those curved mirrors, that can make you appear to be upside down. Like you guys have heard of funhouse mirrors before, right? They're curved mirrors, and they can make things look different than they really are. An image can also be produced inside the mirror, like we've talked about. Like when you look at a plane mirror, that's a virtual image. It appears to be inside the mirror. But a mirror can also produce an image that's in front of it. These are real images. You don't encounter these nearly as much in your day-to-day life, but they exist. And of course, the image in the mirror could be larger than the object. They could be smaller, or they could be the same size as the object. Like you guys have seen those mirrors, like on the side, your side view mirrors on your car, where it says objects in mirror are closer than they appear. It's telling you, hey, I'm showing you these things in a different size than they really are, because those are curved mirrors. And they do that so you can see more around you, not just a picture perfect image of what's right there. The goal is to let you see a lot, not the right size of things. And then those real and virtual images. So real images are produced by converging light rays. So if you make the light rays all meet up at a single spot, then it will produce a real image there. Real images are less common in our day-to-day life. Most things that you see are virtual images, and these are produced by diverging light rays. So light rays that appear to move away from a single point. So what happens is, it looks like they're all coming from one spot, and our brains are able to make an image out of that. It goes, oh, well, it must be over there. So when you see yourself in the mirror, your brain says, oh, well, all the light rays appear to be coming from inside the mirror, so you see yourself inside the mirror. It's just produced by what our brain extrapolates from the light rays that are coming to us. Real images are when you actually are seeing all the light rays converge at a single spot. Real images can be kind of trippy to see. They tend to have like a holographic feel to them. Like we have an example of these that I would show you as well, and it's like a little, looks like a floating hologram inside of this curved disc. So real images, you can project them onto screens and surfaces, while a virtual image can't. You'll only ever see it inside the mirror or inside the lens. Now, I've talked about mirrors some. Let's talk about lenses. A lens uses refraction. So mirrors, their whole thing is light bounces off. It's reflection. Lenses use refraction. This is when light goes through a medium and bends because it changed speed inside the medium. So that's how glasses work. So the lenses in my glasses, light hits the lens and it changes speed because it's a different medium, and it's going to bend. And when it bends, it's going to change where the light goes, and that helps my eyes see. If a lens used reflection, they wouldn't be very useful as glasses because light would just hit the surface and bounce off. You want light to go through a lens. So mirrors use reflection. Lenses use refraction. Now, once again, we do have different shaped lenses, and they can either converge light or diverge light. So convex lenses, the one we see at the top here, these cause light to converge. They will bend light rays to all come together at a single spot. And you may remember that that single spot is called the focal point. The concave lens is the opposite. A concave lens is a diverging lens. Diverging means it makes the light rays all split apart. So converge means come together. Diverge means go apart. So each one of these lines right here represents a light ray. And they're just shown to say, hey, look, this is what it's going to be doing to the light. It's going to bend it and make it meet up, or bend it and make it go apart. So now I'm going to show you a quick demonstration of a diagram that we use to represent what light is doing and how we can figure out what the image would look like. So if we were in class together, I would be having you draw these things. But since we're not, this is all I got. So looking at this right here, we have a concave mirror. So a concave mirror, you can see it's bending inwards. So it's made a little cave right there that the light's going to go into. This arrow right here, the big one that I'm dragging around, this is our object. So the object is going to have light rays that hit the object and then head towards the mirror. So we have our 3 light rays here that I'm going to turn on in a second. And this down here is the image. You see that other arrow right there? That is the image that's going to be produced by this mirror. So if we look at this, see the 3 light rays that I've turned on? All of them are coming from the tip of the object right here. We usually draw them as arrows just because they're really simple. This could be literally anything though. It could be a candle. It doesn't matter. But we draw them all from the same spot on the object. The important thing is you can look at this and figure out what the object would, or the image would be like. Looking at this diagram right here, here's the object. Notice it's an arrow, and it's about as tall as one of these grid squares right here. Well, here's the image. Notice that arrow, is it the same size as the original arrow? Hopefully you've said no. So this arrow is smaller than the original one. That tells us this image is smaller than the object. Remember, the first one is the object, this one is the image. So the image we know is smaller. Is it upright or inverted? Hopefully you've said inverted, because this one is pointing up and this one is pointing down. So we have an inverted and we have a smaller image. And you can look down here at the object distance and object height, and image distance and image height. And that will help you figure out whether or not you're actually seeing a smaller object or a bigger object, same size, so on. Now, looking at these, would you say these are converging or diverging light rays? Hopefully you're thinking converging. If you look at this, the light rays all hit the mirror and they all meet up right here. So we have converging light rays, meaning we produced a real image. So we have a real, inverted, smaller image in this case. And then, of course, you can move it around and mess with it until you have something different. Now, I'm going to put it right on the spot labeled F. So F, remember, is the focal point. That's where all the light rays want to be focused at. The problem is, now I've put the object there. Well, notice that all the light rays are kind of off screen, and look at what it says at image distance and image height, infinity. When the object is at the focal point, it can't focus. An image wouldn't be produced. I mentioned earlier that I had a big mirror that I was going to walk around the class with and show you guys yourselves, and how you start off and you're really big and you're upright, and if I get closer, then suddenly you're upside down. Well, in between, you actually disappear. If you were watching the mirror, as I walk towards you, suddenly you wouldn't see anything. That's what happens when you're at the focal point. No image can be produced at the focal point. That's very important. Let's go to a lens. So here I am at a lens. This is a convex lens. If you notice, the object is still at the focal point. Look at the image distance and image height. It's still infinity. So lens or mirror, if an object is at the focal point, you can't make an image. And then we move it around and ta-da, now I have an image again. So looking at this, the object is about 1 grid square high. Let's do this. The object is 1 grid square high. Would you say the image is larger or smaller? Looks bigger to me. So now I have a larger image, but it's still inverted because it's upside down. And therefore, it's still a real image. You can see the light rays are converging here. So just look at compare the image to the object. That's how you decide whether you're dealing with smaller or larger, inverted or upright. And if all the light rays come together, it's converging, therefore it's real. If all the light rays were to go apart, then you're dealing with, let's see if I can give you a better view of that. See how all the light rays here, they all diverge? One goes that way, one goes this way, one goes that way. If they all go apart, there's my tiny image right there. Then you're dealing with a real image. Or sorry, a virtual image. And now let's go back. And we'll finish up with diffraction. So diffraction, very basic. Light can act as both a particle and a wave, but all we're dealing with right here is a a wave behavior. And waves can bend around things. They can bend around obstacles like you see here at the bottom, or they can bend through openings. This is why like light can come out from under a doorway, or you can hear things around corners. Light bends around the corner. This is why you have a window and light can fill a room even though the window isn't the same size as the entire room. Light comes in the window and bends to fill the rest of the room. Now, since we are dealing with bending, well, different colors of light have different wavelengths. The wavelength is literally like the size of the wave, we can say. So depending on the size, the wavelength of the wave, it's going to bend different amounts. If you have a small opening, a long wavelength is going to have to bend a lot to get through it. And vice versa. So if you have a large opening, a small wavelength doesn't have to bend very much. And there are some real scientific applications of this. The only one Edgenuity gets into is called spectroscopy. Spectroscopy is where you analyze light by splitting it. So the sun, for example, is a really good example of using spectroscopy. Sunlight to us is just white or yellow at best. So if you take that light and you put it through a spectrometer, what it does is it's going to use diffraction to cause that sunlight to bend and split. So different wavelengths of light will bend different amounts, and you can look at all the different colors that are in sunlight. And then you could actually figure out like what elements are in the sun, or rather in the gases around the sun, and then you could use that to figure out what elements your sun is made of. So spectroscopy uses diffraction to bend light based on its wavelength. And this is used all the time in science to figure out what something is made of, what elements you have. So that is your real world application of spectroscopy. And that's all I really need you to know about diffraction and application of it. So that is it for this week. Those are our highlights. Remember, mirrors reflect, lenses refract, and diffraction is the bending of a wave. If you have any questions, post them in Google Classroom or email me. I will also be having office hours on Thursday, so if you have questions, you can pop in there. Remember, feel free to ask any questions you have. I will explain it however I need to. Be sure to like and subscribe, and I will see you guys in the next one.